Hi and welcome back to the channel and Happy New Year. I want to take a few minutes to walk through a few things I've been doing recently within KStars, principally in FitsViewer and Live Stacker, just to give you an update on what I've been doing. So the first thing I've been doing is I've added xisf support to Live Stacker. So xisf is PixInsight's format, or it's an open format, but it's pushed by PixInsight, and if you like, it's an alternative to Fits. So it's a more modern protocol, but obviously Fits is very well established and used by many programs in both professional and amateur astronomy. So what you can do now is you can record subs in xisf format, either in mono or in color, and you can use Live Stacker to stack those. So I've also added an ability to debayer xisf bayered images if you have those. So here's just an example of the Live Stacker with the results of an xisf file that I've loaded. The other thing I've been doing is I've been refactoring the Bayering or debayering process within FitsViewer, which benefits both just regular FitsViewer usage, where you're looking at subs or finished images or whatever you're looking at, and also Live Stacker. So probably the best way to kind of explain that is to start off by explaining the debayering process, and then I'll show you what you can do in FitsViewer and Live Stacker with it, and also go through a little bit of what I've added, which is really to add OpenCV's debayering process alongside the existing legacy process that KStars has used for many years. Okay, so if we just back up a little bit and I'll explain what bayering and debayering is. So this is just an example. This is just an image I've got off the internet of the various, there's 4 of them, Bayer methods. I'm really only going to concentrate on image D here in this example, which is the RGGB Bayer matrix, which is the one that is by far and away the most common in astrophotography. It's the same principle if you have a camera that uses one of the others, but I'll just concentrate on, as I say, image D. So this is RGGB Bayer matrix, and what that means is that checkerboard in image D, if you like, is a grid of pixels that represents your color sensor. Now obviously this is only a few pixels, but in principle this grid would be much bigger in real life on a proper sensor. It could be say 4000 by 3000, let's say a 12 megapixel sensor, but it would just be a repeat of the RGGB matrix all the way over the sensor. So what you get as a result of taking a color image is that each pixel records one value for the image, and what that pixel means is it's either a red pixel, a green pixel, or a blue pixel. So if we take the example of the top left pixel in image D, which is a red pixel, you're going to get one number in the image, and that one number will represent the red value. You won't get a green value and you won't get a blue value because that pixel is just a red pixel. So in your color raw file, you will have, let's say it's a 12 megapixel camera, you'll have 12 million numbers, and each of those numbers will represent a red, green or blue value at that pixel location. Now the debayering process is a decoding process, if you like, that will take each pixel and it will create a red, green and blue value for that pixel location. So let's take the top left pixel in image D, which is red. The debayering process will come along and it'll say, okay, I've got a red value, so I'll use that, but I haven't got a blue or a green value, so it will create a green value and create a blue value. How it does that we'll get to in a minute, but the whole purpose of the algorithm is to create these values. It'll then move to the next pixel, so let's say it's a green pixel, so it'll say, okay, I have a green value because that's the raw data, but I don't have a red value and I don't have a blue value, so the algorithm will create a red value and it will create a blue value, and it'll do that across all of the pixels in the file, and that'll be the end of the debayering process. So typically what you would expect to see is your raw file will have a certain size. When you debayer it, you would typically see a size that is 3 times the original raw value, because what it's done is it's taken one value at each pixel location in the raw file, and it's finished with 3 values at each pixel location, so your file size will increase by a factor of 3. So that's kind of debayering 101. So let's go back to an example, and I'll show you a bit more. So if I just bring up a color image, this is a raw sub. It's been debayered in the FitsViewer. Now if I bring up the debayering utility, which is Control D, you get this little window. Now I didn't actually know this existed until a couple of weeks ago when I was looking at the code, so I suspect there's probably quite a few people using K-stars that don't know it exists. But anyway, Control D, if you have an image that is debayerable, will bring up this window. If your image is mono or it's a planar color image that is not debayerable, then you won't get this image, this window. The other thing I'll do, I'll just bring up the statistics window, which is quite useful. I'll show you why in a bit. So what I can do is I can change the algorithm and debayer in different ways. So prior to my change, K-stars uses a debayering library called libdc1394, which is, I think it's quite a well-used library, but it's a very old C library. It's, I don't know, 30 plus years old maybe. It's you know, it's very robust, generally works very well, but it's very old. So what I've done is I've added another engine, which is OpenCV, and you know, we can sort of come on to look at some of those algorithms in a bit, but basically the OpenCV algorithms are much faster, and I think they're probably slightly better as well, but I think, you know, it would be good for people to you know, test it out and give me some feedback. So by default, prior to you know, any changes, if you're using the current live version of K-stars, you'll be using the libdc 1394 engine, and you'll be using its simplest method for debayering, which is nearest. And you know, it just basically looks at the nearest neighbor pixels of a similar color in order to work out the pixel values in other locations. The other items on here really are for just playing around, so you could change the debayer filter. If I do that, it'll probably come up with some horrible colors. Yeah, okay, it's gone magenta, which is not very helpful because the image wasn't taken with a this GRBG filter. It's an RGGB. You can also put offsets in. I mean, I'm not going to get into that. It's more for a debugging type situation if you wanted to play around with this, but it does let you sort of play around with the values. These values are typically taken from the Fits header, so the values for the X and Y offsets and for the filter, the RGB or whatever it happens to be, they're typically Fits keywords that are written into the sub, and K-stars will read those Fits keywords and apply them appropriately. But just as a debugging tool, you could, if you wished, play around with it. I think the most useful thing is to play around with the with the algorithm and see what happens. So basically, there's a bunch of algorithms here. As you go down the list, they get typically more sophisticated, but also they take longer to run. So it's the interplay between, you know, how good is good enough versus, you know, how slow or how fast, you know, do you really want to go. I've added another engine, which is OpenCV. OpenCV has got its own algorithms. There's really only 3 of them, but the VNG algorithm only works on 8-bit images. So if you try and use it on 16-bit images, it will just revert to bilinear. So really, for most people, I think it has just 2 algorithms, bilinear and edge aware. I think from what I've seen, edge aware is slightly better. It is minimally slower, literally only a few milliseconds slower, but probably that it is, I think, in my opinion anyway, slightly better. So I think this is a better algorithm. And you can just, you know, rerun these, and, you know, it'll re-debayer that particular image for you using the algorithm. So if you zoom in a long way, you know, let's I don't know, let's focus on this sort of reddish star here in the middle. Just zoom right in as much as I can. And you know, you can have a look by playing with the various algorithms as to, you know, what you think is the you know, is the best. As I say, I think from my perspective, the OpenCV algorithms look to be at least as good, if not better, than the libdc 1394, and they are quite significantly faster. The other thing that the libdc at 1394 isn't so good at, I think on the edge of the frames, the algorithms I think tend to throw in 0 value pixels. So you'll see up here, for instance, which is why I brought up the statistics, the minimum values in each color is 0. Now that's just not realistic on this particular image, and I think it's probably a slight issue with the way libdc 1394 works. If I just use one of the OpenCV algorithms, you see I get a, you know, I get a non-zero value. So I think for that reason OpenCV is slightly better, but I'd be interested to hear what people think. So why is OpenCV faster? Well, let me just show you some stats. So I ran this, so basically I ran each algorithm on my PC and I ran it several times, took an average. So these are the, whatever it is, 6 libdc 1394 algorithms. So the fastest one is this nearest one, which is the simplest one, which on average was taking, you know, 260 milliseconds, so roughly a quarter of a second, whereas the 2 OpenCV algorithms, so bilinear and edge aware, are taking about, you know, just over 70 milliseconds, so, you know, nearly 4 times faster. So obviously the OpenCV stuff does run a lot quicker. The reason it runs more rapidly is that OpenCV takes advantage of various hardware acceleration like CUDA that many chip manufacturers make available now. So in order to take advantage of things like that, you have to code it to take advantage of the hardware acceleration. libdc 1394 was written way before a lot of the hardware acceleration came on the scene, so it's not hardware accelerated at all. So it's really just doing a C loop through all of the pixels rather than doing some of the more sophisticated vectoring that OpenCV does. So OpenCV will be quicker. Depending on what chip you're on, it will be a lot quicker or maybe marginally quicker, but I wouldn't expect it to be slow on any processor. So I think generally, as far as I can see, the OpenCV algorithms will be better for color images. So anyway, you can play around, using this and see what you prefer. What I've done also is into settings, I've added a couple of new parameters. So there are Debayer options here, one for just regular images in the FitsViewer and one for Live Stacker. So you can select what your preferred engine and algorithm is for each of those. I'm going to default this so that for images it's going to be what it always has been in K-stars, which is the libdc 1394 and nearest. And then for Live Stacker, I'm going to default it to use edge-aware on OpenCV. So for folks that don't want to go in and fiddle with it, that's what you'll get in the next release. But obviously you can change it if that's what you want to do. And I would encourage, if folks with color cameras, to have a look at this, because I don't have a color camera, so it would definitely benefit from some extra testing. And then over time, if we feel that the OpenCV algorithms are at least as good as libdc 1394, then maybe we default everything to OpenCV, and maybe in the fullness of time think about decommissioning libdc 1394. So I think that's about it. So I'd be very interested in any feedback. So have a play and let me know.